with the transition to our next speaker. How do we understand the complexity and how do we statistically test for the thousands of data points, the many modalities, and the embeddings that come together in these various approaches? And so up next to speak on this topic, Nikitas Koussis, a postdoc from University of Newcastle. Thank you for joining us. Looking forward to your talk.
Yeah, so this is it's actually quite good, Boris. Thank you, Boris, for leading me into leading us into the kind of the methods section of the session. So, is this going to come up on the?
Can you switch? If you click on swap display. Swap display?
So, yeah, many of you may already know about the eigenstrapping method, but for those who don't know, it's it takes eigenmodes and uses a lot of it resamples them by rotating them across null space, and it came out as a desire from myself and Michael Breakspear to refine the process of spatial resampling, simplifying a lot of these processes and making something comparable to the spin test. And how I like to analogize this is the spin test on multiple spatial scales, very many spatial scales. And it can replicate the spectral properties of brain maps while randomizing higher order features in the data set, and like phase randomization can for time series. So how we usually analyze these things, we take two brain maps, or two or more, say our fMRI activation maps and myelin map here, correlate them, and then we can perform a spatial permutation test because we probably not aware of the ground truth or association between these things. So in the past, it has been brain smash and spin test. Sorry. So as we expect the null hypothesis to be that the association between these maps the mean is around 0, and the variance of that distribution is related to the spatial autocorrelation of those maps. So what ends up happening with the spin test, and one of the major drawbacks is that because the medial wall is there and we haven't really come up with a way of resolving to get rid of it or integrating the subcortex somehow, that information is lost by rotating it into the surface. So we lose about 30% of the data. So we take if we're doing the correlation, we mask it at the points that have NANs, and so that ends up removing about 30% of the data. It also doesn't really randomize that much. So if we take just a face here and project it to the cortex, spin that cortex and project it back, a lot of the higher order features like the face here, the nose, eyes, they're all there basically, just a bit distorted, but they're not randomized much at all. And that maybe there's some higher order features in the data in brain maps that we should be randomizing in order to come up with a way of testing whether there's nonlinear effects or not. So I'll just skip through a lot of this, but there's nothing here that you guys probably haven't already seen. So we have the Laplace-Beltrami operator operating on Newman boundary conditions, and we solve the Helmholtz equation on the cortex. And what we have is the Pang et al. Paper, basically. But we can, what we can do is multiply the modes, the modal matrices within a group structure, and I can talk more about the group structure outside. I won't have time to cover that much. because we'll try to get to a bit of a tutorial in a minute. Multiply that, the group structure in the modes, and multiply that by a rotation matrix, and then reconstruct maps. So what we do is decompose the maps into the geometric eigenmodes, and we've got the, where's the laser? There it is. So this is the eigen decomposition. We have the coefficients here, beta, and the eigenmodes psi, and the maps are made up of these. This is the group structure. So we've got the number of groups, and then within that group we have the number of modes, and they come in this, like, group 0 has 1 member, group 1 has 3 members, and so on. So then we take each group, rotate them, we do a normalization step, and then that projects it to an equivalent spherical space, and we rotate this spherical space, and then multiply back through by this factor. This is just the square root of the eigenvalues. And doesn't work. Okay. Then we reconstruct the eigenstrap maps. So we call them eigenstrapping. Yeah. This rotated modes over here can then recreate surrogates that have the same spatial autocorrelation as the original map. So then there's an extra step here. It's resampling, amplitude adjustment resampling. So just basically taking the values from the surrogate, sorting the values in the original map, and then slotting in the values from the original map into the sorted values over here. So this is just a visualization of that process. It just rotates. I think I like that animation. So we end up with projecting back to the cortex, and then surrogate maps then have spatial autocorrelation. So this is HCP data, and we've managed to reconstruct this variogram nicely. And then we decided to test the false positive rate. So the false positive rate is, we expect it to be 5% or around 5% in maps, and just as a property of the statistical test we're doing. So a p-value of 0.05, we expect 5% of the time we're going to get a false positive. So we simulated maps with spatial autocorrelation in Gaussian random fields, and tune this parameter alpha to increase the smoothness. I'm not going to go into the details about why that can tune the smoothness, but we tested our null. We generated nulls for each null method, so eigenstrapping, brain smash, spin test, and calculated the false positive rate. So this is just a demonstration. Nice test at saying our null distribution of eigenstrapping surrogates increases in width as the smoothness increases. This one, sorry, my slides are really out of order. Where's my marker? There. So as we increase in smoothness, it lies, like 0 would be completely noise, white noise, and then it starts to get a bit smoother. And as you go towards fMRI maps, it remains around 5%. And so we're like that. And then as it goes even further, you can see it starts to climb a bit. And out here, there's not really many maps, like maybe EEG or PET data, but these are maps with like a 60 millimeter full width half maximum. They're quite smooth. But yeah, for the vast majority of brain maps, the false positive rate remains nominal at 5%, and it always is lower than the spin test and much lower than brain smash in the same tests. And one of the advantages for eigenstrapping as well, and unlike the spin test, is we can do this on arbitrary surfaces. So we've done this for 3 subcortical maps in the paper, the thalamus, hippocampus, and striatum. So we take cortical, subcortical gradients from, I believe, Tien's work, or anyway. Then we tried to replicate the maps using the eigenstrapping surrogates, and we get pretty good results. And the change in Moran's eye is much lower. So Moran's eye is a global measure of spatial autocorrelation. So we ideally want the change to be 0. We can see it's mostly around 0, but it does much better than Brain Smash there. And this is the video about what I was showing before, randomizing complex spatial patterns. So we quantified that using LTP, defining a number between 1 to 9 as to what's similar. Where is it? There it is. And you can see, like, if you put this in this grayscale kind of edge detection format, the spin test, it remains very similar. Eigenstrapping completely messes it up. The variogram for these maps is exactly the same, but the original image, the surrogates is far different, very, very different to what ends up coming out of the spin test. So this is a nice way of just quantifying those differences. Something else that we've been working on, well, not actively at the moment, but maybe someone can pick this up, is fixing modal rotations. So we can generate spatiotemporal surrogates here. And what I'm referring to is just taking each of the time series elements, doing the eigen decomposition, rotating the eigenmodes, multiplying back through, and we end up getting, for each volume, because everything in space is fixed, what we're actually doing is multiplying the coefficients every time, doing that for each volume, and you end up with a surrogate time series. So then we can do things like calculate the power spectrum and see whether that power spectrum is actually significantly different in the presence of spatial autocorrelation or not. Like, is there something particular to that data set? These are very rough ideas, but I'm sure there's someone out there that's inspired to pick this up. I don't know, I think it's very interesting. So by accounting for linear spatial relationships, eigenstrapping nulls can be used to infer nonlinear activity. So I'm gonna risk it, unlike Boris, and just try to get this workshop running. I wonder if I actually have time. How much time do I have left? Oh, we'll try it anyway. So you may be able to, if you want, you can follow along in the link in the Google Drive, but I'll just go through. A lot of this is just background information, but the main property we're sort of exploiting here is that the eigengroups in the cortex, so these are the groups we're going through before, there is a separation in the amount of energy that they have, and they never cross in these things, and so they are in the lower order modes especially. You're never going to find it if you rotate them that they end up crossing nodal lines or boundaries. Anyway, it's a nice mathematical kind of formalism there that we can actually kind of do this. So there's just an example here, and I've already downloaded it, thankfully, so hopefully this shouldn't break. So we can plot, I've just downloaded the first principal component from the Allen Human Brain Atlas, and Daniel's first intrinsic functional organization gradient from his 2016 paper. And we plot them, and they look pretty different from each other. And when you correlate them, you end up with a fairly strong negative correlation. So there is like a negative association between these things, and the direction is arbitrary, so you could equally say that there is a positive correlation. So eigenstrapping has one parameter to tune. It is a number of modes to use in the decomposition. So you want to use the number of modes that replicates the smoothness in the map and no more than that. Otherwise you start fitting noise. So we've written some functions to be able to do that, and you can estimate it using the full width half maximum. So for the principal gradient of gene expression, you get 37 millimeters, and for the functional gradient, you get 30.7 millimeters. So this is the main thing. You want to find the wavelength of the modes, the characteristic wavelength, that is smaller than the minimum of the full width half maximum of the maps. So for this, it's 899 modes. So just go through and plot a few surrogates. And we'll just wait for this. There we go. 1, 2. Oh, maybe I'll just plot 2. Stop. There we go. So they're pretty similar. I don't know. I can't really tell the difference. Don't know about yourself, but so then we can also calculate the full width half maximum just to do a sanity check on whether they're actually similar or not. And we can see it's 25 millimeters, so it's actually a little bit smaller than the functional gradient. So maybe we go back and tune the number of modes, but that's fine. It's really not that much different. So then eigenstrapping, you can just, once you have that eigen class there, and going through the notes is, I'll leave people to do that on their own time, but you can generate 100 or 1,000, whatever, however many surrogates you think you need, and calculate a null distribution using that. So we just do a bit of statistics, and it will plot the null distribution in a second. It was not this slow before. Why is this taking so long? There we go, okay. So then the original correlation sits on this, like it sits on the tail there, and then we calculate the p-value, or the p-value there. P-value is less than 0.01, so you would say that's pretty significant. The maps are anti-correlated above and beyond what would be expected by chance. And that's the critical thing, is that you're testing the hypothesis that these are just associated because of smoothness and associated because of spatial order correlation. So it's directly testing that null hypothesis there, which is the goal for, I think, a lot of these fMRI maps and gene expression maps and so on. So then we can go through, so a little bit of parameter sensitivity analysis as well, just to make sure that we're actually replicating the right property there. So we can just change the number of modes, and I've just changed it to 50, and it's probably a good idea to sort of do this as a sanity check as well. So generating the 1,000 there, and wait for that. There we go. So there's a bit wider tail as well, so it will give you a denser distribution there, but there's a wider tail, and so the p-value for that now is probably going to be a bit bigger. So it's still significant, but the p-value is a lot higher than it was before. And maybe if you're doing lots of these analyses, you'll find that it falls out when you do FDR correction or whatever. So then, I just want to, so we got to do these questions, and I wanted to just pass it out to you guys. Why is it important that eigenstrapping preserves the original map's spatial autocorrelation? What would be the consequence of breaking spatial autocorrelation when generating brain maps? Is it because SA preservation ensures the surrogate maps maintain the same local smoothness? Breaking SA leads to underestimation of variance and inflated false positive rates. Is it because SA preservation guarantees the global mean remains identical? Because it affects the definition of ROIs? Or is it D, because preservation is only needed for visualization? So who says A? So we got a few, okay. B? C? Or D? We got one. It is A. So yeah, you need to ensure that it does, the underestimating the variance and inflating the false positive rates are linked ideas there. Because you'll find that a correlation that normally would fall within the null is not falling within the null because you haven't increased the width of that distribution enough. So I won't even bother with the graph. I thought I might plot a graph of how many people. It'd be like Who Wants to Be a Millionaire, how many people answered A, B, C, and D, but I only got like one, maybe 4 in each thing, so I'm not going to do that. So outline the main steps in which the eigenstrapping algorithm uses the surface eigenmodes to generate surrogate maps that retain the same spatial spectra. Is it A, compute the surface Laplacian or LBO eigenmodes, project the map to these eigenmodes, randomly rotate the modes within each frequency band, and then reconstruct the map via the inverse transform? Or is it B, run a principal component analysis on the map values? Is it C, randomly permute the vertex values within the mask, leaving the values outside the ROH unchanged? Is it D, smooth the original map with a Gaussian kernel based on the mean edge length and add white noise to match overall variance? So who says A? And B? I should hope no one else says anything other than A. Unless maybe you've nodded off a bit. So then, after computing the test statistic on the original map and on each of the surrogate maps, how do you construct a null distribution and calculate a one-sided p-value? Is it A, build the null by collecting a statistic from every surrogate map? Is it B, fit a normal distribution to the surrogate statistics and calculate the p-value from the z-score? Is it C, perform this paired t-test? Or D, bootstrap the original map values? This one's a bit harder, actually. I'll be interested to see which way it goes. So who says A? 3, 4, 5. Yeah. And B? No one. C? Okay. And D? Okay, it's pretty split between A and D. So it's actually A. Build the null by calculating the statistic and then compute the p-value as a proportion. So I'm actually a bit ahead of time, but that's okay. I think you guys are probably keen for lunch. So I will end my talk there. Thank you.
Are there questions before we break for lunch? Any pressing questions? There's one. There's one, yeah? Okay. There's one, first of all, thank you for a wonderful talk. And really addressing a very challenging statistical topic within the field that I think we're all itching for interesting answers and ways to address this problem. One of the questions that was posted online, I don't understand the rationale that enables spinning each mode, also how this method solves the medial wall problem. But this may have been more in reference to spin tests, I suppose, but yeah. Any thoughts about that?
Yeah, so because the modes can be calculated with that Newman boundary, I didn't go into this because it would take up so much time, But because we're doing it without incorporating the medial wall or masking that out, essentially, the modes can be considered in a separate space to the cortex. And there's a little bit of a nuance there that I'm happy to go into outside or at another time. But mathematically, it remains essentially identical. There's really no difference between incorporating the medial wall or leaving it out, but we're masking it when we do the transformation. As for, what was the other part of that question? The first part?
Oh, the rationale that enables spinning each mode.
It's essentially, it's transformation that retains orthonormality. So there's really no reason you can't do it.
There's no reason you can't do it. We've got a question? There's plenty of time, so if there are any questions.
So yeah, for the spin test, that the problem is medial wall, right?
And also the has a higher FPR as well, false positive rate.
Okay, but to solve the medial wall problem, can you just do a flat map of the brain and spin the flat map?
Yeah, I think that's one of the proposed solutions. I'm not too sure what the end result was of that. I'm not sure if it's better than just spinning it automatic, like the way it's already done. I'm not sure if anyone's tried that.
The more important issue is the higher order effects, right?
Yeah, of course. Yeah. That's the other part of it, like nonlinear effects that might affect textures in there that you don't destroy.
Yeah, hi. If I understood correctly, you visualize it in 3D by essentially you're rotating a hypersphere of like 100 and so.
Yeah.
So do you see a way of potentially using this approach to try and randomize only specific like spatial frequencies in the data and saying like try to permute only, like keep large scale consistent, but and then only.
Yeah, absolutely. That's a great point. You can absolutely randomize different spatial scales, keeping some fixed and some others randomized. Say your first group, you want to just keep the large modes fixed and then rotate the higher order modes because you want to get an individual variability or whatever hypothesis you're interested in. I think this is going to, hopefully, maybe it'll grow and other people will have some great ideas and inspiration out of it.
Because I was worried that if you have to use so many dimensions in the end, you're already covering pretty much all of the spectrum.
Yeah.
Or can you just
I'm not sure I understand. Maybe we can chat outside, yeah. Okay. It's not that high. I think it is a bit slower than spin test in the full, so there's two different methods that we use to resample. One is, I didn't show it here, but it's a bit quicker. We managed to get a speed up using nearest neighbor permutation matrices. So instead of calculating the rotated modes every time, you pre-calculate the rotated modes and then just find the modes, find the nearest neighbor rotation matrix that gets you to those rotated modes. And that's like a re-indexing procedure. So then you just multiply through by that permutation matrix on the values, and it gives you that surrogate, as if you've done the rotation. So that's a bit quicker. It's about, so you go from about 5 to 10 minutes on the free surfer 32,000 surface, free surfer FSLR, to about 2 minutes, 1 to 2 minutes with that speed up.